Hi everybody! Today we're going to be going over sedimentology and stratigraphy. This is the second lesson in our Strat playlist, and in today's video we'll be going over texture versus structure of sedimentary rocks, just to give an idea of what that means, because grain sizes are a texture, whereas structures are very different. And then we'll briefly discuss hydrodynamic and diagenetic textures, then grain sizes in detrital rocks, classification based on grain size, binary names, because most rocks have more than one grain size and we kind of have to specify a little bit further. And then what grain sizes tell us about a rock's formation process, how grain sizes become reduced during transport and abrasion processes, and what those transport processes are. So first and foremost, what is texture? And what's the difference between the texture of sedimentary rocks and the structure of them? So texture deals with the size, the shape, and the arrangement of the mineral grains in the rock. And some textural features are simple, like grain size and angularity, but some are a bit more complex, such as porosity, which depends on grain size and angularity, as well as packing and sorting of the grains. So texture has a lot of different things that it contains in its definition, and all of these features are small scale that you can study in a hand sample or thin section of a sedimentary rock, whereas structure refers to large-scale features of sedimentary rocks that sometimes can be seen in hand sample, but more often you need an outcrop to see because they're that large scale. As we can see, the sedimentary structures here in this outcrop are cross-bedding, and down here in these hand samples, we don't really get to see a lot of structures except maybe the sandstone here has some lineations, but we can't tell what kind they are. There's no real crossbed, so maybe if it was in an outcrop, we better be able to see what kind of structures are going on there. There are two main types of textures that we kind of hinted at in the last video, the first video in this Strat playlist, that are common in sedimentary rocks, and these include hydrodynamic textures and diagenetic textures. And a lot of the sedimentary rocks have both, unfortunately, because that makes it harder to classify them. But like we talked about in the last video, sedimentary rocks can either be clastic or detrital or chemical. Those clastic and detrital sedimentary rocks, like sandstones or conglomerates, typically form by rock fragments of previous sedimentary igneous or metamorphic rocks that are transported to a basin or somewhere where they start to accumulate, and then they're buried, compacted, and lithified, and they form rocks. This transport of material by some sort of fluid, whether it be air or water, that then eventually accumulates somewhere to make a rock, is how detrital and clastic rocks like sandstone and conglomerates, and therefore they're defined as having hydrodynamic textures, whereas those that form directly from precipitation from solution, either as the primary deposit or as secondary precipitation in the pore spaces of detrital sediments as cement, is clumped into this diagenetic texture category. And these diagenetic textures are also sometimes called crystalline. And then the less common textures that we might see in sedimentary deposits are biogenic textures, when the rock is just fully biogenic, made by biology, or colloform, when produced by coagulation of a gel. But in this video, like the previous one, we will be focusing on the hydrodynamic and diagenetic textures in sedimentary rocks, and not so much the difference between the two, but actually the hybrid of both, and how we can classify those types of rocks, and how that relates to grain size, and how we can use grain size to understand the formation processes of sedimentary rocks. So first, let's define the major grain sizes in sedimentary rocks, specifically clastic or detrital sedimentary rocks. So things like conglomerates, sandstone, siltstones, and shales. So first we have the largest grain sizes, which are all clumped into this one term called gravel. Gravel is defined as any grain larger than 2 millimeters in diameter. And obviously there's a lot of grains that are larger than just a measly 2 millimeters. So this has a lot of subcategories to it. The grain sizes that fall under gravel include the largest grains, which are termed boulders, and these are larger than 256 millimeters or around 10 inches. And boulders are the term used for rounded large grains, whereas blocks are the term for angular grains that are over 256 millimeters. So same size parameters, just angular versus rounded. And that'll come into play when we talk about breccias versus conglomerates, because the only difference mainly is their angularity. And you might think, why does that matter? Why do we have to have a whole different rock term for angular versus rounded material? Well, it has to do with how the rock forms. If it's more angular, obviously it went through less transport. And if it's more rounded, it went through more transport. And that can help us greatly into understanding the rock's history and its depositional environment. Beneath boulders and blocks is cobbles. Cobbles are anywhere from 64 to 256 millimeters. And then we have pebbles between 4 and 64 millimeters. And then we have granules between 2 and 4 millimeters. And these are all over 2 millimeters, so they're still all underneath the larger category of gravel. Sand is the next size down from gravel, and it also has subcategories because sand as a whole goes anywhere from 1/16 of a millimeter to 2 millimeters in diameter, and very coarse sand specifically is 1 to 2 millimeters. Then coarse sand is defined as 1/2 to 1 millimeter. Medium sand is defined as 1/4 to 1/2 millimeter. Fine sand is defined as 1/8 to 1/4 millimeter. You probably see a pattern occurring. And very fine sand is 1/16 to 1/8 millimeters. And below very fine sand, we have silt, which is 1/256th millimeter to 1/16th millimeter in diameter. And that is very, very tiny. Lastly, we have clay, which do not even try looking for this with your naked eye because you will not see clay or silt. Honestly, very fine sand and down is very hard to determine without at least a hand lens, which is basically like a magnifying glass for those unsure. I have the hand lens I use linked in my description if you're curious. And typically even a hand lens isn't enough to identify clay. Clay grain sizes are less than 1/256th millimeter in diameter, and this is just very tiny. Honestly, the way that my Strat teacher taught us to recognize clay is not by looking with your eyes, because you're not going to get anywhere with that, but instead by looking with your mouth. It sounds a little gross, but you know, the stereotype of geologists licking rocks isn't totally untrue. We do actually do some rock licking when we know it's safe and when we know we have to. For example, when trying to identify clay, it has a texture very similar to chocolate. If you take a little bit, just a little, don't take a whole mouthful, my goodness, just a little bit, and try and grind it beneath your teeth. If it's not at all gritty and it has a chocolate texture, it is clay. If it has a tiny, tiny, tiny bit of grit, it is too large to be classified as clay, and it is then silt or very fine sand, and you're going to have to do some more analysis to determine what size of grain you're looking at. But rock licking and tasting aside, let's talk about the rock types that result from these grain sizes. So the rocks that are formed by consolidated gravel are called conglomerates, but like I mentioned, the roundness or angularity matters in this terminology because the rocks that contain consolidated angular gravel are termed breccias. So conglomerates are a bit more rounded than breccias. Next, we have sandstone, which contains very coarse, medium, fine, or very fine sand. That's what sandstones are made of. So there's a variety of different sandstones, and some sandstones have a variety of those different sizes. And then we have siltstones, and that's obviously consolidated silt. And then we have mudstones or shales, which are consolidated clay or mud. And yes, sometimes when I'm eating chocolate, I do think of mudstones and shales. And I hope that now you will also do the same. But obviously, like I mentioned when I was introducing the topics in this video, rocks don't all contain one grain size. What if a rock has both gravel and sand? Then what do we call it? Conglomerate or sandstone? How do we name these consolidated mixtures of grain sizes? sizes? Well, we have to use binary naming if we want to get that specific. For example, here we see that if a rock contains over 80% gravel, it is classified as conglomerate, no matter what any other constituents are. But if you want to get more specific and you see that over 10% of it is sand size, but it's still mostly gravel size, then you can call it a sandy conglomerate. But if we flip that and say it's mostly sand size, but contains over 10% gravel sizes, then you can call it a conglomeratic sandstone. You can also just use the name sandstone if it's over 80% sand sizes, regardless of the rest of the constituents. And then if it is mostly sand and contains over 10% silt, you can call it silty sandstone. If it is mostly silt and contains over 10% sand, you can call it sandy siltstone. If it's over 80% silt grain sizes, it is siltstone. And you can probably see where we're going with this. If it has over 10% clay, but is mostly silt, it is clay siltstone. If it has over 10% silt, but is mostly clay, it is silty clay or silty claystone or silty mudstone or silty shale. There's a lot of names for clay-containing rocks. And lastly, if it's over 80% clay, you can call it claystone or mudstone or shale. But what is the significance of understanding what grain sizes a rock contains? Well, we can tell a lot about what those grains went through to then become deposited and form the rock that they formed by looking at the grain sizes and the distribution of grain sizes in a sedimentary rock. How does this work? What do I mean? Why is this so? It's because grain sizes and their distribution within a sedimentary deposit are affected heavily by transport. Whether it be through water or through air, transport of grains decreases the grain size downstream or downwind. And my book said this was grain weight loss, which I thought was a really funny terminology because, humans obviously love the term weight loss. And I just thought it was weird terminology to use for rocks, but it also made me think, oh, maybe I should go and throw myself down a river then. But regardless, it's unfortunately not so simple that we can just say grain size reduces downstream with increased transport. Unfortunately, exactly how much grain size is decreased during these processes is hard to determine because sorting of grains is also occurring. You might have seen my previous depositional system videos where I've talked about transport of grains through water or air through different transport processes, like coarse grains rolling on the bottom sediment or ground rather than fine grains being suspended in the air or water and transported that way. This causes a sorting of grains, and the more transport, the more sorting that happens, and you might get very poorly sorted sediment, which might not have been transported very far, or very well sorted sediment, which probably went through a lot of transport. Another thing that happens with increased transport is angular grains become more rounded, and we'll talk a lot more about this in the next video, but all of these things are happening and can help us see how much transport and how much throwing around those grains have dealt with before they were finally consolidated into this rock that they now are in. But getting back to the topic of grain size specifically, grain size reduction during transport is heavily affected by several factors. The first one is size of the original grain. This is a very important factor for determining the final grain size because obviously if you're talking about reducing the grain size of a big boulder, it's not going to be very much smaller by the time it's been transported very far because one, it can't be transported very far. It's super heavy unless it's a really, really strong flow. And we have that right here, violence of action or violence of river or flow that is involved. And so that's another factor that goes into determining how much grain size reduction occurs in the final grain size of the grain. And another thing we see here is durability. So not only does the size of the original grain matter, but also the durability of the material of that grain. Because think about quartz versus carbonate for a second. Quartz is going to be way more durable and going to go through way more transport before it's even reduced a little bit in size or rounded a little bit. And so quartz is going to tolerate more transport than carbonate grains. Carbonate grains, we always know if we see really well intact phosphorus fossils in a rock, it probably hasn't traveled very far. It probably was not transported for very long, if at all. And if we find fragments that are pretty well broken up and pretty well reduced, it probably underwent a little bit of transport, but still not much. Because if we were to subject carbonate grains like this to transport processes, they're not going to last very long. They will get fragmented up. They're more susceptible to both physical weathering and erosion just because their hardness is much less than quartz, for example, but they're also more susceptible to chemical weathering and dissolution. So they just don't last long in transport processes. Another factor that affects the reduction of grain sizes during transport is the bed surface composition and size. For example, sand versus gravel beds will have very different effects on grains that are traveling through in that water and becoming reduced. Also, you can imagine gravel beds versus moss-covered gravel beds can also have a different effect on the abrasion that's occurring to grains being traveled by that river, because anything that's moss-covered or covered by biological material is probably going to be a little bit gentler than just pure rock surfaces that are kind of going to act as like sanding down the grain in a way. Another factor that plays a role in reduction of grain size through transport is the shape of the original grain. So not only does the size of the original grain matter, but also the durability of the original material, as well as the shape of the original grain. And this will play an even bigger role when we talk about roundness through transport in the next video. The last factor that plays a major role in the reduction of grain size during transport is the duration or distance in which the grain is transported. Obviously, like we talked about, carbonate grains are not going to last very long, and quartz grains will last much longer. And so the reduction of those grains is going to change drastically depending on how far they're transported. So we don't just use grain sizes to classify different rocks. We can also use grain sizes to really understand the formation processes that went in to forming these rocks. And grain sizes are heavily affected, like I just mentioned, by transport and depositional processes. Abrasion and grain size reduction can occur in all transport regimes, not just fluvial, but also glacial transport regimes. Glaciers can pick up and carry sediment, and they can abrade the sediment beneath them. And alluvial transport regimes, shore phase transport or swashing in the swash zone, and wind transport, and more. Basically, any depositional environment with whatever transport process they have abrades grains and affects their size. But transport and physical processes aren't the only processes that affect grain sizes. Diagenetic processes can also affect grain size through dissolution and etching. And actually, the finer the grain, the greater the possibility of diagenetic dissolution and further reduction of grain size, because fine grains have greater surface area available for these diagenetic reactions to occur in the pore spaces that contain water and are in contact with those grains. But even with these diagenetic processes, the more significant size changes occur during transport and deposition. So grain size is still very diagnostic of its transport history and depositional environment. And like we mentioned a couple slides ago, the major factor that controls grain size reduction and distribution or sorting during transport is the original size of that grain. And that is because that grain is going to travel differently or be transported by different mechanisms depending on its original size. For example, traction can occur to large boulders that are just rolling through a riverbed or in an aeolian environment or any other transport regime we just mentioned, whereas saltation can occur to slightly smaller pebbles or sand grains that are going to bounce along the ground or that riverbed. And then suspension transport can occur to very fine material, and even dissolution into the solution as ions and being transported that way and then precipitated elsewhere can also occur for transport mechanisms depending on the size as well as the composition of the material. And all of these processes and how we can determine depositional environment or system based on the final rock that we have and its texture and structure and grain size and all of that is discussed in my fluvial, aeolian, glacial, and delta depositional environment videos, as well as a lot of the other depo environment videos I have on my channel. So go check those out if you want to know more about how exactly we determine depo environment based on these grain size and other features that we see in the final sedimentary deposit. And if you want to know more about the diagenetic processes I mentioned, and specifically the diagenetic reactions that can occur and what secondary minerals and chemical precipitates that they can cause to form in pore spaces or as replacement minerals in sedimentary deposits, you can watch my microbial weathering video, my carbonate burial and diagenesis video, and that is all in my geobiology playlist if you want to check those out. I'll link the playlist up here in the right corner for you. And that's it for today's grain-sized focused SED-Strat video. We did have an introductory SED-Strat video when we talked about the general types or classes of sedimentary rocks and their general characteristics like their internal fabrics. And then we're going to talk more about grain shape in the next video, like roundness and what that can tell us. And then we'll talk more about all of these other topics. You can pause the video and check out these different titles of videos or tentative titles of videos that I have coming up in this SED-Strat playlist, or you can just head to my channel and check it out to see if I have those videos out by the time you're watching this one. So lastly, I just want to mention that my major references for this video include the SED-Strat book by Sam Boggs, shown here, as well as Sedimentary Rocks by Pettyjohn, and both of these books are linked in my description below if you want to check those out for yourself. And that is all I have for you guys, so thank you so much for watching, and I can't wait to see you guys next time. Bye!